All right, let's dive straight into this explainer. Welcome, everyone. Today, we're unpacking an algorithm that absolutely shook up modern machine learning. Now, if you've spent any time at all looking at data science competitions or doing real-world predictive modeling, you've for sure heard its name. We are, of course, talking about extreme gradient boosting, universally known as XGBoost. We're going to break down why it was created, how its mathematical brain actually works, and why it became the absolute go-to tool for structured data. Our journey today really starts with this idea. Every revolutionary technology begins with a simple question. How can we make something already great even better? See, before XGBoost came along, we already had gradient boosting, and it was a fantastic algorithm. It was successfully predicting weather, diagnosing medical conditions, forecasting finances, the whole shebang. But as the world changed and datasets exploded into the millions and billions of records, traditional gradient boosting hit a wall. It could be super slow, it demanded heavy memory, and sometimes it just memorized data instead of actually learning from it. So XGBoost wasn't built to replace gradient boosting, it was built to evolve it. To really grasp this evolution, we're going to follow a pretty clear roadmap today. First up, the blueprint. Second, the foundation. Third, the navigation system. Fourth, the construction process. And finally, the finished building. Okay, let's jump right into section 1, the blueprint. Why build XGBoost in the first place?
Well, as datasets just grew massively in size, those older algorithms simply couldn't keep up. So think of it using this chef analogy. The X in XGBoost, it just stands for extreme, as in extremely optimized. Traditional gradient boosting is kind of like a solid cook working in a basic, ordinary home kitchen. XGBoost is that exact same chef using the exact same mathematical recipe, but we've just dropped them into a state-of-the-art, highly optimized professional kitchen. They can just work so much faster, way more consistently, and with way fewer mistakes.
But here's the catch. Cooking in a high-tech kitchen only works if you actually know what a good meal tastes like, right? This brings us to a really fundamental question. How does XGBoost actually know whether it's making progress or if it's just making mistakes faster? To answer that, we have to look inside the brain of the system.
Which brings us nicely to section 2, the foundation. The objective function. The objective function is essentially a GPS destination for XGBoost. It literally guides every single decision the algorithm makes. But to get there, it balances two competing goals, kind of like a scale. On one side, it has the loss function, which is trying to minimize prediction errors. But on the other side, it has a regularization term. This acts like a strict budget to stop the model from becoming unnecessarily complicated. You see, earlier algorithms mostly just cared about that first thing, reducing error. But XGBoost, it's constantly weighing prediction accuracy on one side and total simplicity on the other.
So why does that simplicity matter so much? It's absolutely crucial to prevent a massive problem we call overfitting. Imagine two students taking a math test. Student A actually understands the underlying concepts. Student B? Well, student B just memorized 10 years of past exam papers. Now, they might both score a 98% today, but when faced with a brand new, unseen question tomorrow, student B is going to completely fail. Machine learning can make this exact same mistake. Regularization ensures XGBoost behaves like student A, seeking true generalizable understanding rather than just blindly memorizing the training data.
Okay, so we have our GPS destination set, and we know we want an accurate but simple model. The next question for the algorithm is navigating the actual terrain. If you're standing in a super dense forest trying to reach the absolute lowest point in a valley, you need to know two things: which direction goes downhill, and exactly how steep is that hill.
And that leads us to section 3, the navigation system, gradients and Hessians.
This is where XGBoost introduces some seriously intelligent math to course-correct its errors. Traditional gradient boosting only really looks at the gradient, which you can think of as the steering wheel, telling you which direction reduces the error. But XGBoost, it also looks at the Hessian. Think of the Hessian as the accelerator pedal. By using both of these together, XGBoost knows the exact direction to steer and exactly how hard to step on the gas without overshooting the target. It's a real game changer.
With this incredible navigation system in place, the algorithm begins building out its decision trees. But as it's building, it constantly faces a choice. It literally has to ask itself, is adding a new branch and splitting this data actually worth the effort? Let's look at how it answers that in section 4, the construction process. Similarity and gain. Before XGBoost splits a leaf into new branches, it grades the current leaf using something called a similarity score. Imagine dividing a giant classroom of students into focused study groups. You want students with similar strengths working together, right? The similarity score uses our friends from earlier, the gradient and the Hessian, to measure exactly how coherent a leaf is. If the data points inside the leaf behave in similar ways, boom, it gets a high score. If they're completely random, it gets a low score. Once it has those similarity scores figured out, XGBoost evaluates the potential split through a really elegant three-step process. First, it calculates the similarity scores for the old leaf and the potential new leaves. Second, it calculates the gain. Actually, think of gain as basically the return on investment. It asks, if I make this split, is the improvement large enough to justify that complexity penalty we talked about? If the answer is yes, the branch is built. If the gain is too small, step 3 kicks in, pruning. The algorithm simply rejects the split. This ensures the tree only grows when it absolutely adds meaningful value. All right, let's step back and look at Section 5, the finished building, XGBoost in the real world. When you put all this together, it becomes incredibly clear why XGBoost completely dominated platforms like Kaggle for years. I mean, linear regression is beautifully simple, sure, but it struggles with complex patterns. A single decision tree is easy to visualize, but we know it easily overfits. But XGBoost, it effortlessly handles nonlinear relationships, controls its own complexity, and it natively handles missing data right out of the box. For structured, tabular datasets, it is often just the absolute best tool for the job. And the real-world applications of this are just staggering. In environmental science, researchers are using XGBoost to predict PM 2.5 air pollution concentrations during major wildfires, churning through massive datasets of temperature, wind, and vegetation. In finance, it's detecting fraudulent transactions in literal milliseconds. In medicine, it predicts patient survival rates. In sports, teams use it to analyze biomechanics and flag injury risks. Because it perfectly balances extreme accuracy with computational efficiency, it's uniquely versatile across almost every data-heavy industry on Earth. But as we wrap up our analysis today, I really want to leave you with this vital reminder. A tool is only as powerful as the person who knows when, where, and how to use it. Listen, XGBoost is a masterpiece, no doubt, but it's not magic. If you're analyzing unstructured data like images or audio, you're honestly better off going with deep learning. If your dataset is tiny and you need total 100% interpretability to explain it to a stakeholder, a simpler model might be best. True mastery of machine learning isn't just knowing how an algorithm works under the hood, it's having the wisdom to know exactly when to pull it out of your toolbox. So, as you take this knowledge forward into your own projects, ask yourself, will you use your models just to memorize the past, or will you leverage things like regularization and gain to build models that truly understand the future? Because that's the real power of XGBoost. Thank you so much for joining me on this explainer. I really hope this deep dive has given you a whole new appreciation for the engineering marvel that is extreme gradient boosting. Keep learning, and I'll catch you in the next one.